active metals just happen to be reactive enough that they would immediately react with water. Right, that's about it. Right, I don't care that you know which ones are active metals. I just expect you to recognize that active metals means they react with water immediately. So certain species will do this right away. Pretty much everything in the group 1 will react very violently, very quickly with water. Right? Then just kind of as a side note for the record, no one was like, oh, you're not going to talk about the answers? Okay. I was just curious. Like, didn't you want to know?
Yeah.
Yeah, okay. Jeez. Man, there's never a method to my madness. So if we went through and looked at this, we'd get lead by itself, followed by zinc sulfate. So what we're doing is we're taking a look at where they fall on our activity series. We're comparing lead to zinc. So we find lead. Where is it? And we find zinc. Which one's higher on the activity series? Zinc. Because it is more active, it wants to be with something. So when we go through and look at this, where is zinc with something? It's in the product side. Okay? We could do the converse of it. Lead is less active, meaning it wants to be away from everything. Where is lead away from everything? On the product side. Okay. So which side of the reaction is favored? Where did I underline? Product side, which means? Yes, reaction happens. Okay. Next one, we're comparing magnesium and nickel. If we were to go through and predict this one out, we get the magnesium with the nitrate. Did I do that right? Yeah. And then nickel by itself. Have I predicted correctly?
Yes.
No. Nickel's not going to be charged. Remember when we run the single replacement, the one that was in a compound and ends up by itself goes neutral. Okay? So it's all by itself as a solid neutral compound.
Yes.
So that looks okay. But I said it's wrong. Meaning nickel's not the problem. Magnesium nitrate's the problem. What's the problem? It's not balanced. The charge on nitrate is a -1. The charge on magnesium, a +2. That formula is incorrect. To make it correct, what do I need to do? I need 2 nitrates. Okay? So I've predicted my equation should a reaction occur. Well, to figure that out, we look for the magnesium and the zinc on our list. There's zinc, nickel. Magnesium is more active than nickel. Where is magnesium with something else? On the product side. Nickel is less active than our magnesium. Where is it by itself? Product side. Should a reaction happen? Yes. Is that good so far? Yeah, everybody's like, yeah, I got it right. No, okay, well. You should review. This is how we use an activity series. Right? For those of you being like, well, you didn't talk about it. It was in the textbook, and I held office hours. Lots of office hours. Just briefly. So, the next one. What did we produce? Silver with the chloride and aluminum by itself. Is this correct? No? What's wrong with it? What's not balanced? The silver chloride. What's the charge on chloride? A -1. What's the charge on silver? +1. A +1. Is that formula correct? Yeah. Yes. Because people were talking about it, you were probably saying, well, isn't there a 3 there? Shouldn't that 3 go over here?
No.
Why is the 3 there?
To balance it with the aluminum.
To balance the aluminum. Is the chlorine with aluminum anymore? No. So we shouldn't be using it. Okay. Is the equation balanced?
Not yet.
No. So I could go through and balance the overall equation. The products themselves were correct. So if we wanted to go through and balance the equation, We do need 3 chlorines, which means we're going to need 3 silvers, and now we have a proper balanced equation. Look at that. I could even have done this. Ta-da! See, 3 silvers. Got rid of the decimal? Nah, never, sorry. It's kind of telling when people laugh when other people are laughing. Okay? So, should this equation happen? Okay, well, we go back through and do our comparison. We're comparing silver to aluminum. There's aluminum, there's silver. Aluminum is higher on the activity series, which means it wants to be with somebody. Where is aluminum with somebody?
On the reactant.
On the reactant side. Silver's lower on the activity series, meaning wants to be away from everybody. Where is the silver away from everybody? On the reactant side. If I mix these reactants together, what do? Nothing. They do not react because they're already in their happy states. There's no reason for them to do anything. This is a no reaction. Okay. Last one will be a fun one to try and go through and balance. So let's not worry about balancing it. We get our gold with our copper. If we go through and again do our comparisons, we're going to compare gold to copper. Copper is higher in activity, meaning it wants to be with something. Where is it with something? The reactant side. Gold is lower in activity, meaning it wants to be away from everything. Where is it away from everything? On the reactant side. Should this reaction happen? No. It's all on the reactant side. If I mix these reactants together, it's already in its happy state. So no reaction happens. Kind of makes sense? That's how we use our activity series. Okay? This is kind of neat too, because this also goes to explain, at least the activity series goes to explain, right, at least the historic selection of currency. Right? Like currency, right? What is our money based off of?
Gold.
It's based off of actually gold. It's starting to change a little bit now, okay? But at least it was historically based off of gold. And you could only print the amount of money that you had gold for. You could make multiple divisions, but that just meant your money lost value. That's why you can go to certain countries and they end up paying with billions of their dollars because they've done so many subdivisions of the money and so much printing of it that it's lost all of its value. There's nothing to back the currency. Okay, so gold was traditionally the thing of value. Why would we have put so much value in gold?
Pretty.
We could go with pretty. We could go with conductivity. Okay, it does actually have more conductivity than, say, something like copper, or even silver for that matter, but copper works fairly well. Why else might we have chosen it?
It's rare.
Let's take a complete flip. Notice gold at the bottom. Let's switch it up and use lithium. Lithium is now what we've decided to base all of our world currencies on. Okay, so we got Fort Knox of lithium. Okay, what does a terrorist do to destroy our currency system?
There's some water.
They throw some water on it. What happens when lithium hits water? It reacts and becomes an ion, dissolves in the water, and it falls through the drains into the ground, and we've now lost all of our currency that backs it. Gold was a valuable material, not just because of it looks pretty, okay, or even some of that electrical conductivity, because electrical conductivity, quite frankly, didn't exist in our precursors. Okay? It's because it didn't react with anything. We think about copper. Copper could be pretty too. We can make copper things that are actually pretty cool looking. But what happens to it? It reacts, and it carries a different color associated with it. So if we had instead used copper jewelry, everybody would have stained fingers and ears and whatever because it reacts to create a different material that we could see. We didn't like that aspect, so that's why we stuck with materials that didn't react. Okay? What are our typical sources of jewelry? silver, gold, platinum. All at the bottom of our activity series. They're non-reactive metals. Okay? That non-reactivity is what translates to our value behind them. They don't change. Okay? That's what we use as our sense of kind of relationships. Okay? We use a ring to symbolize marriage. Why?
It doesn't react with others.
It continues on itself. Right? It doesn't end. Right? If you think about marriage, the whole point of marriage is that you're with that person for the end of your life. A ring makes good sense for that because it never ends. Okay? If a symbol for a marriage was a pencil, eventually you grind down on the pencil enough and what happens? You throw the pencil away. That's a horrible metaphor for marriage. Okay? It may be more accurate, but that's irrelevant. Okay? So we've picked these things to represent that unchangeability. So when we're looking at currency, that's ultimately what's happening. We can see that in our activity series. Yes?
Is that why, to tell the difference between like fool's gold and like regular gold, you test it with like nitric acid?
So one of the ways that you could test gold for its validity was running different reactions with it. While gold is very low in the activity series, there are some things that can make it react and turn into an ion. Those are very limited things, okay, but we can do it. Okay, there's a substance known as it's referred to as aqua regia. Aqua for water, regia for royalty. Okay, why royalty?
It's rare. It's noble.
It's rich, and what do rich, noble people tend to have a lot of? Gold. Aqua regia is because it is a substance that dissolves gold. There's very few substances that do, but it does dissolve gold. Okay? There was a story about a Nobel Prize winner during Nazi Germany who was about to get invaded by the Nazis, had his gold Nobel Prize, and was like he didn't want to lose the gold for it, but he figured there was no way he'd be able to get it out of the country. So what he did in his lab is he dissolved it in aqua regia and then left it on the shelf. The Nazis came through to try and steal whatever was of value. All they see is a solution that looks clear. I'm not going to steal a container of water. It's kind of dumb. So they leave. He comes back afterwards. His lab, for whatever reason, wasn't destroyed, and he was able to reclaim the gold out of the solution. Okay? So there are substances that can force reactions to happen. Aqua regia happens to be one of the more famous ones for gold. Okay? Kind of not either here or there, but kind of just fun stuff. So cool. Activity series. It explains world currencies. Used to explain world currencies. Now it's built on nothing.
Why is the hydrogen involved?
So if we go through and look at this, where's lithium? What can you tell me about lithium? Most active, yes, keep going.
In the first column.
First column, okay, potassium.
First column.
Sodium. Magnesium. Not in the first column. What do they all have in common? They're metals. Okay, I was waiting for someone to say they're all on the periodic table. Okay. They're all metals. Metal, 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 metal. Non-metal. Why is hydrogen being incorporated in an activity series where we're typically referencing metals?
It's the exception.
It's not actually even an exception. We can do activities for non-metals as well. Hydrogen tends to be the 0 point based on how we rank all of the activities. Okay? So that's why hydrogen's incorporated in this. Okay? Why else is hydrogen incorporated in it? Come on. Work with me. Oh, come on. Active metals. What are active metals reacting with?
Water.
No. Nope. They are reacting with hydrogen. They're doing a single replacement reaction where they're taking hydrogen away from water and putting it with the sodium. Okay? We're doing a single replacement reaction. Okay? Because when we take our metals and we drop them into water and we see this reaction, well, they're doing a single replacement. This can't be just for the metals. Hydrogen must also be included in it. Right? if we expand this out to electricity and redox reactions, okay, or electrochemistry, if you were going to move into, say, 152, we would then take this a step further to realize all of our elements can be incorporated into something like an activity series. But what we're referencing then is the electric potential. Okay? So we change the name behind it, but it's still the same underlying current. Hydrogen just happens to be one of those things that we could quickly test and see with water. That's why hydrogen shows up in our cells. Okay? Yes?
So I was looking at the activity series in the book, and it's different from the ones up there for some reason. It put silver and then mercury and then gold. But I don't think that's correct. Like, so which one should we reference?
So one of the things that we might find with it is we're going to get some slight variations because of their exact electric potentials. Okay? Nothing that I put up here was something that I generated, so I can't take credit nor blame, sort of. I can take blame for curating it because I put it in there. Okay? This table, again, you'll see some slight variability from different tables to others, but for the most part, it should hold pretty darn close to true. I'm going to bet if you look up the exact potentials for silver and mercury, they're really close, and that's why they're oscillating back and forth. Okay, depending on which table you're using. They should be pretty static. Okay.
For the test, are you giving us the table or do you not answer?
Do I expect you to memorize a sequence of metals for activities? Okay. So some people might be already jumping on the answer. I already know the answer to that. That's good because you looked at the front page of the exam. Even on exam 1, guess what's on exam 1? A modified activity series. I do give it to you. Okay. It will also be given to you on the final as well. The final is in a slightly different format that matches more like the textbook. We still got to have some discussions about that within the department.
Oh yeah, by the way, when is the practice exam due?
The practice exam never has a due date. So number 1. When should you have the practice exam always done?
Before the test.
The Friday before the test. Always. Okay? Because at that point you can get the answers, you can get the feedback so that you can study to prepare. Okay? Can you use the practice exam as homework questions?
Yes.
Yes, which means when would that be due?
Friday.
Every even Friday. Okay? So there's no official due date for the practice exam. You can use it for the homework. Okay? Other questions? Okay. This is where things are going to potentially get a bit dicey because what we're going to move up to is Chapter 17, our Oxidation and Reduction chapter. The reason we're making this jump at this stage has to do with our single replacement reactions. If we went through and looked at that lead and zinc reaction, what is the charge on the zinc in the product? Zinc sulfate.
+2.
It is a +2. How do you know it is a +2? It must balance out the sulfate's -2. Okay? What is the charge on zinc in the reactant? 0. How do you know it's 0?
It's by itself. It's just the neutral atom.
So it's just by itself, it's the neutral atom. So you're telling me it's 0 because it's 0.
It has to have reason.
It doesn't balance with it.
It doesn't have to balance with anything. Well, that's a possibility. What if I had written this? What's the charge on the zinc?
Now it's 2.
Okay, why all of a sudden are we now getting a +2 there, whereas before it was 0?
You don't have anything written in the top right.
Where is the charge always specified?
Top right.
The top right-hand corner. In our reactant, what is written in the top right-hand corner of the zinc? Nothing, which means 0. What is written in the top right-hand corner for our zinc sulfate? Nothing. Why are you telling me zinc is a +2?
You have to balance it out.
That charge is referencing the top right-hand corner for that whole compound. Okay? Sulfate, I know, is a -2. For that to equal 0, the zinc must come in as a +2. Okay? So I'm able to determine the charge, per se, on the zinc based off of the overall charge directly given to me. The charge is always, always, always given to you. Okay? There is not a single exception to that. Okay? If the zinc is a +2 here and the zinc is a 0 here, does anybody notice anything kind of bizarre about that? Okay. Zinc to have a 0 has how many protons? Those of you not looking at the periodic table, that's why you're having a hard time with it. 30. How did you come up with that? The atomic number is literally the number of protons. If it's going to be zinc, it has to be 30. How many electrons would it have? 30. How do we know that? The charges have to balance out to get me an overall charge of 0. When I move over to the product side, how many protons does that zinc have? 30, because if it wasn't 30, it wouldn't be zinc. How many electrons does it have? It has to be 28 electrons. Why does it have to be 28 electrons?
+2 charge.
It's a positive 2, which is why I had to lose electrons. So when I ran this reaction, what happened to the zinc?
It lost 2 electrons.
It lost 2 electrons. Have we seen electrons in an equation before? Should rhyme with no.
Yep.
Should have picked a different word than no. It is no. We have not talked about electrons in a balanced chemical equation before. That's because they don't show up in balanced chemical equations. Why do they not show up in balanced chemical equations? Not quite. What's that? They actually have a huge bearing on the balance of the equation. Electrons are matter. You cannot create or destroy matter, so they must be balanced. Why do we not see electrons in a chemical equation? Where do we find electrons in this room? Sort of.
Everywhere.
If I want to find some actual electrons, where would be the easiest source for me to find electrons? Let's go to the electrical outlets. Electrical for electron. That's literally what's coming out of the outlets, is a bunch of electrons. Are those things stable?
No.
No. That's why they're behind an outlet, and we tell people to not put forks in them. Right? If electrons were just floating around, we would tell people don't wave forks around in the air. Right? They're coming out of the electrical outlet, so we have to watch out for those. We don't stick forks in there because that sucks. Are you guys asking about sticking forks in outlets? Don't do it. Okay, I just want to make sure. Don't do that. It's not pleasant.
Wait, is it coming from experience?
Possibly. Okay, don't do it. That is a horrible, horrible idea. Okay? They're unstable. I don't include electrons in a balanced equation because they are so ridiculously unstable that they could never exist on their own. When I'm looking at a balanced chemical reaction, I'm saying the things that exist on their own. So it's counterintuitive. I can't include electrons in there because they don't exist on their own. Okay? They have to be stabilized internally by something else. Okay? But I just lost 2 electrons. Well, where the hell do they go? Okay? If we look at the rest of the chemical equation, what else do we find? We find that the lead started as a +2 and it went to a 0. What happened to the lead? It gained 2 electrons. So what we're talking about in the single replacement reaction is the transfer of electrons from one species to another. Okay? That type of reaction is what is known as a redox reaction, or an oxidation and reduction, or reduction and oxidation. The order ultimately doesn't matter, but there's so much ations and oxtions in there that we usually condense it down, and redox sounds better than ox-red. Okay? So you'll hear people refer to them as redox. Okay? neither one can happen just on their own. They must happen in conjunction with the other. Why?
Batteries conserve.
We're talking about the transfer of electrons, and if electrons can't exist on their own, I have to get them from somewhere and they have to go somewhere. That's why I tie those two concepts together, and they're always referenced as redox. They're done together. Okay? Really what these are pushing to is this new concept of oxidation state or oxidation number. Okay? And because that GIF is already bothering me and I'm not the one looking at it, let's try and pause that so it stops moving. Okay? Oxidation state and oxidation number are referring to the balance of electrons and protons on an atom. But what was charge?
The whole unit.
The balance of electrons and protons in something. The charge is looking at the larger scale. It could be virtually anything. The oxidation state is referring specifically to an atom. Okay? So it's a question of specificity in what we're referencing. Okay? If I take the oxidation states and sum them all together, okay, for an individual species, I will then get the balance of protons and electrons across a larger unit, which would then mean I'm looking at the charge. Okay? So they are tied to each other, but they are not exactly the same. Okay? The rules that we've generated or I've said are kind of modified for this is that you should know the charges on your ionic compounds. Okay? Because if you know the charges on the ionic compounds, you can then break apart the ionic compounds into the individual pieces, which could simplify your solve. Okay? After that, oxygen will have a -2 oxidation state. This means when I put oxygen near anything else, it is going to steal electrons. Why would oxygen steal electrons from anything else? Well, so does sulfur, so does chlorine, so does bromine, so does iodine, nitrogen, phosphorus, carbon. Why oxygen being a -2? So do all the other elements. There was a concept that we talked about that I said was incredibly important and that we needed to hold on to it because it's super, super valuable both in bonding and interpreting oxidation states. No, somebody else mumbled it. As you guys are pointing at each other, that was nice. Electronegativity. Oxygen is the second most electronegative element, which means when I bond oxygen to anything, what is it going to do? Steal the electrons, except when? There are two exceptions. Nope. When oxygen is bonded to hydrogen, it steals the electrons from hydrogen. With the most electronegative. I just said oxygen was the second most electronegative. What's the most electronegative? Fluorine. If I put an oxygen next to fluorine, guess what happens? Fluorine takes the electrons from oxygen. Oxygen carries a positive. What's the second exception? Bonded to itself. If I bond oxygen to oxygen, they're now equally fighting for the electrons. Okay? That's also going to change its oxidation state. Right? So the next big part, the sum of the oxidation numbers equals the charge on the unit. Okay? Written out another way, the number of the element times the oxidation state plus the number of the element times the oxidation state, et cetera, et cetera, et cetera, equals the overall charge. Does that look really familiar?
Yes.
Yeah. In fact, that looks almost identical to the thing I told you that you should be using when doing nomenclature. And I said that was going to become important. This is why. What we're looking at is the balance of those electrons and protons. When we're doing nomenclature and figuring out how much to get of each, we're balancing those charges. If you don't acknowledge that that's what you're going through and doing, when we move to oxidation state, you're now having to relearn the wheel. Okay? If you acknowledge that it was a balance of charging, hey, you're set and ready to run. now all you're doing is doing a subtle tweak to it. Instead of saying the charge on an element, it's now the oxidation state for an element. Okay? And it's now the exact same process. Kind of, sort of? Okay. So if we move to the crossover method, the textbooks, we just shuffle numbers around. We have no concept of what's happening. The whole point is balancing charge. Okay? That's why the crossover method is dumb. It removed an understanding that only worsens life further on down the road. Okay? So, where does this ultimately lead for us? And since nobody ever turns around, I'll just pause. What we would be asked to do is to look at this equation and say, well, what happened? Okay? And we could go through and try and classify it according to the chemical reactions we've talked about. Anybody have any guesses? Kind of looks like a single replacement. Carbon's bonded to oxygen in both the reactant and the product, though, right? Okay. Combustion relies on the reaction with oxygen gas. There's no oxygen gas. Neutralization, I need an acid and a base. There's no acid or a base. Decomposition requires one thing going to two. Combination, two things going to one. Double replacement. Well, what's exchanging to react with the iodine? It doesn't really fit any of those categories. Okay? So what we're trying to address here is there's other reaction types. This particular reaction type is a redox reaction. It's a reduction and an oxidation happening together. Okay? It best mirrors what would potentially be happening in a single replacement. It's just not easy to nail those things down. So we just ignore that and call it redox. Okay? How do we know that this is redox? We could say, well, it didn't fit in any of the others, so it must be that box. Okay, that's possible. We could reference that the atoms lost or gained electrons. But to do that, what would we need to know? No, but right idea. The oxidation states. So when we say you need to be able to determine the oxidation states, this is why. You need to be able to look at this equation and quickly determine the oxidation states for each element. Okay? And on which side of the equation should you determine the oxidation state for the element? All sides. Everywhere. Okay? So on the reactant side, I have 3 elements. On the product side, I have 3 elements. I have to determine their oxidation states on both sides of the equation. Because oxygen is showing up in a compound on both sides of the equation, I know the oxygen's oxidation state will be -2. Okay? Because the oxidation state for oxygen is always -2. Did it gain or lose electrons? No, nothing happened to it, nothing exciting there, so I can just say no change. Okay? What happened to the iodine? Okay. Well, I have 2 iodines. I have to solve for the oxidation state, X, plus 5 oxygens times its oxidation state, -2, and this has to equal?
0.
Why does it have to equal 0? That is the charge that is specified in the upper right-hand corner for the formula. It may not equal 0. You have to do what is specified. Okay? So now when we go through and do this, we could go through and solve, and we would find that X equals, try again, +5. Okay? Can't do the algebra in your head that fast? That's fine. Write it all down. Okay? If we go through and do the iodine on the product side, well, how many elements are there in that one? Or iodines? There's 2. Dang it, I have to solve for the oxidation state of the iodine. Plus, what's the next element? Okay, so I can say equals. What does it equal?
0.
Why is it 0?
Specify.
Upper right-hand corner, there's nothing written. It's 0. What is X? X equals 0. So anything in its elemental state will have what oxidation state?
0.
0. What happened to the iodine in the course of the reaction?
Gain 5.
Gain 5 electrons.
It had to gain 5 electrons to go from a positive 5 to a 0. Okay? That can be confusing. I'm starting at a 5 and I'm going to 0. What did I do to the number?
Decreased.
I decreased it. And yet what am I saying happened to the electrons?
You got them.
I gained them. Whoa, what?
They have negative charge.
Electrons are negatively charged. Remember how I said that negative sign would be a real SOB? Here it is. So it gained electrons. Where did it get those electrons from? If the oxygen didn't... If the oxygen did nothing with electrons, carbon had to supply the electrons. And if I go through and determine the oxidation states for the carbon, what do I find? +2, +4. To go from a +2 to a +4, what did I have to do?
Lose 2 electrons.
I had to lose 2 electrons, and there we go. So we could now constantly go through life referencing these things as gain of electrons and loss of electrons. So the name of the chapter becomes Gainost reactions. Right? Everybody get it? Gainost? Yeah, right? Not redox. But we call it redox. Why? It's reduction and oxidation, but it's referencing gain of electrons and loss of electrons. So we invented a term to represent this gain and loss. That's the whole point. Okay? Yes.
Can you give a map for carbon, please?
Sure, and actually I'm going to hold that for a second because that question may be being asked again in the back. Do you guys have a question?
How'd you get the carbon 2 and carbon 4?
Cool. Exact same question. Let's take a look at the carbon. We'll call it the blue carbon, determine its oxidation state. So on the reactant side, it's CO. How many carbons? 1. What's its oxidation state? X plus 1 oxygen. What's its oxidation state? -2. What's the overall charge?
0.
How do I know it's 0? Upper right-hand corner. 1 times X is?
1x. So it's x.
Thank you. 1 times -2?
-2. So it's 2.
X equals a +2. Yes?
Yep.
Okay. It looks like you're looking at work. Is that true? You guys tried to draw it out? No? Okay, well then I'm just going to throw it out there for giggles anyway. Why did I not reference the 5?
It's telling you how many COs you have.
This is the oxidation state of an individual atom.
Okay, the oxidation state of an individual atom where?
The reaction study.
In a molecule. What does the 5 mean? I have 5 molecules. I don't care about the 5. The 5 is just telling me I have a whole bunch of these. The oxidation state is referencing one of them. I don't need to translate the 5 in. Okay? Let's just say for giggles, you're like, but I want to. How many carbons would show up?
10.
How many carbons would show up? 5. How many oxygens would show up? Someone shouted it out over there. And X equals the exact same answer. The reason I don't reference going through and doing it that way is more often than not, you take that 5 and you apply it to which element? Just carbon. Remember, the number in front applies to everything afterwards up to a mathematical operator. Okay, so when we're determining oxidation states, I don't care how many of that compound there is. I just count how many that element is in that compound. Make sense?
Yes.
Okay.
If
That 5 does kind of bother me. I'm going to fix that while Frank asks his question.
carbon only lost 2 electrons, how did iodine gain 5?
Talk about that too, but we aren't there yet. What happened to the carbon in the product? Because the question was looking at the oxidation states for the carbon all the way through, presumably, right? Okay, so let's take a look at carbon in the product. Where does carbon show up in our product? CO2. How many carbons are in that?
1,
1. What's its oxidation state?
X,
How many oxygens?
2,
Oxidation state.
-2.
How do you know it's a -2?
Always this.
Oxygen will always be a -2. For the sake of this class, I won't even ask the exception stuff. What does it equal?
0.
I would accept overall charge a little bit better than 0, but 0 is okay. We can go through and set it up. X minus 4 equals 0, and I get X equals positive 4. Hallelujah, look at that, it matches. Cool, right? So, the next question came out. What happened to iodine? What happened to iodine? It gained electrons. How many electrons did it gain?
5.
It gained 5. Where did it get those 5 from? From carbon. What happened to carbon? How many electrons did it lose?
2.
Last time I checked, 2 electrons does not equal 5 electrons. Is that possibly what's causing some confusion in the audience? Maybe. Okay. Did I really only lose 2 electrons? Why are you saying no? Someone jumped on that no right away.
Because there's several molecules, each of them loses those 2 electrons.
Each of the carbon monoxides loses 2 electrons. How many carbon monoxides are there? 5. How many electrons did carbon lose?
10.
Times 10. Sorry. 5 times 2 lost 10 electrons. So that's 10 and 5 last time I checked. That's not true. There's 2 iodines. How many electrons did iodine actually gain? 10. Our electrons do balance out. Okay? Okay, so cool. Good questions on that kind of balancing and recognizing that math didn't add. 2 and 5 aren't equal. That was good. I like it. And I'm not being sarcastic. Like, that was good. Questions about what's up there so far? Okay. As you're taking pictures, can I delete? Gain of electrons. Okay, what happens to the oxidation state when I gained electrons? It went down. Give me another way to describe something going down.
Decreased.
It was reduced. When I look at the gain of electrons, my oxidation number was reduced. Gain of electrons means reduction. And when I look at loss of electrons, my oxidation number increased, so it was oxidized. Yeah, that doesn't make any sense. What was oxidized? Carbon. How many oxygens are bonded to the carbon in the reactant?
1,
How many in the product?
2.
What did you do to the number of oxygens connected to our species?
Oxidized it.
We oxidized it. We increased the bonds to oxygen. An oxidation reaction gets the name oxidation because we noticed that when we reacted the species with oxygen, oxygen increased bonds to that compound. So we called it an oxidation. Historically discovered first, based off of physical observations of it reacting with oxygen. Once we processed a little bit more knowledge and understood something about electricity, we realized something else was going on. That's why we bring in the term reduction. Okay? So, if we look here, we've got fun stuff. You are responsible for understanding how to determine your oxidation states. Okay? You are then responsible for being able to acknowledge how it changed through a reaction, being gaining or loss of electrons. You are then responsible for knowing that the loss of electrons is oxidation and the gain of electrons is reduction. This is a lot of individual pieces to stack and all put together, but that's what you have to do. Right? There is a mnemonic device that can be helpful to help you remember oxidation and reduction. Leo, the lion, says, grr. It's phenomenal. It's great. It's environmentally friendly. We're talking about cool animals. Who doesn't like lions? Okay? And they growl. It's fantastic. Leo says, grr. Loss of electrons is oxidation. Gain of electrons is reduction. Right? It's fantastic. Did anybody learn anything else? Yeah, oil rig. Who taught you that one?
You
And-
mentioned on
Well,
the
you mentioned it.
Effing biologist taught you that one. Oxidation is loss. Loss of what? Reduction is gain. What am I gaining? Okay. When I gain weight, I'm certainly not feeling like I was reduced. Okay. They're referencing the electrons. It becomes implied, and we get the stupid oil rig. Okay. And I will continue to call that stupid, and I've called it stupid to plenty of people's faces that insisted that oil rig was valid. It's not invalid. It's just dumb.
Yeah, you made a lot of big deal
Okay.
during the video.
Yeah, and I'll continue to make a big deal of it. Okay, that's not environment. And like, who tells you this? It's freaking biologists. What do biologists study? Life. And what are they telling you to memorize? Death. Like, seriously? It's the biggest conflict of interest ever. Okay. Ultimately, I don't care how you memorize it. You need to memorize it. You need to know that the loss of electrons is oxidation, and you need to know that the gain of electrons is reduction. Okay. Cool. Make sense?
Bingo.
You're like, stop dying about it, right? Yeah, couldn't get any worse.
That question.
That was, wow.
We also introduced this concept of the agents. Okay? An oxidizing agent causes something else to be oxidized. Okay? So if I'm an oxidizing agent, I make you get oxidized. What happened to me? You're oxidized.
You're less oxidized.
If you were oxidized, what happened to you? You lost electrons. But if I caused you to lose electrons, what happened to me? I gained electrons, which means I was reduced. Right? The oxidizing agent is the species that was reduced. Yes. Okay? So if we're referencing that ing, so if you see these weird like English things, ings and ants and stuff like that, they're causing a shift in this. It's effectively a spy, hence the spy versus spy reference. If you didn't get it, don't worry about it. Okay? Your oxidizing agent causes something else to be oxidized, which means it had to be reduced. So when you look at a chemical equation, you can decide what species do the oxidation states. Then look to see how they change. They gain or lose electrons. Then label that as oxidized or reduced. Then label that as reducing agent or oxidizing agent. Okay? All of these things stack.
And this all started with nomenclature.
I don't know I go that far, but yeah.
You're an organic chemist, how well do you anti-oxidants work?
I don't want to open that can right now. Okay? So if we went through with these equations, we could go through and identify the oxidation states. Okay? So for instance, that first one. Tin in the first on the reactant side is a +2. The iron's a +3. You should be able to determine those oxidations very, very fast because they aren't right there. I don't quite accept that, unless you're saying because I drew the answer. They aren't in the upper right-hand corner. What's in the upper right-hand corner? The charge is in the upper, blah, blah, blah. Man, the upper right-hand corner. But because there's only one element there, the oxidation state will equal the charge. Okay, so it becomes a trivial analysis. Okay, so you should be able to determine those quickly. Okay, we could then go through and say, well, what things changed? Tin went from a +2 to a +4, which means it lost electrons. Because it lost electrons, it was oxidized. Because it was oxidized, that means it caused something else to be reduced, which means the tin was a reducing agent. Yeah, don't you love that one? Okay? That is exceptionally confusing. I completely grant you that. Particularly because what I'm noticing by looking around, and this is cool because you're all listening to me, that's fun. Okay? There's only like 2 of you asleep, that's fine. Nobody's writing any of that down. Each of those steps is a cognitive leap that's going backwards and forwards with those minus signs. If you're trying to keep track of that all in your head, you will make a simple mistake. The instant you make a simple mistake, you just screwed up the entire process. by writing down each of those stages, you minimize the chance for that mistake. Okay? And that's where it becomes helpful to write it down. Okay? So if we move to the next one, what is the oxidation state for the copper?
0.
Okay, 0. This is again one of those trivial ones. Okay? What is the copper oxidation state in the product? +2. Again, kind of a trivial one. Say that again.
It lost 2 electrons.
Okay, so we could go through and say it lost 2 electrons right there. Okay? If it lost 2 electrons, it was oxidized. And because I know that ings are weird, if it was oxidized, I know it was the reducing agent. Okay? So if I was asked for the oxidizing agent, it's the NO3 minus. Did I write oxidizing agent yet? No. So how did you get to that answer?
It's the only other thing in
There's only 2 things. All we got to do is figure out the easy one, and the other one must be the other answer if we were wrong. So do the easy stuff first on a test. On the homework, what should you be doing? Do all the freaking work. Okay? Put it all together, process through all those individual pieces. Should we go through and do it with the nitrogens?
Yes.
Oxidation state for the nitrogen. This one I have to solve for. There's 1 nitrogen, X, plus 3 times a -2, Y -2.
Oxygen's always negative.
And then this must equal 0, right?
No, equals negative.
Good. It must equal a -1 because the upper right-hand corner says it's a -1. I can now go through and solve X minus 6 equals -1. X equals plus 5. What did I say X was? The nitrogen. What is the oxygen? Okay. We go through and look at the product side. 1 times X plus 2 times a -2, and then this equals, of course, a -1.
No.
Why is it a 0?
Specified.
Upper right-hand corner doesn't show it's a 0. X minus 4 equals 0. I get X equals 4. What did I say X was? Nitrogen. What is the oxygen? -2. The oxygen did nothing. What happened to the nitrogen? Okay, to go from a +5 to a +4, it had to gain electrons, which then means it was reduced. Because it was reduced, it caused the other thing to be,
Oxidized.
which makes it
Oxidizing agent.
Perfect sense. Well, they're always going to be the same.
okay.
So it's just the nitrogen, the oxidizing agent?
So that's a good question. If we were going to talk about the species that was reduced, okay, or the atom that was reduced, our answer is going to be nitrogen. If I ask for the oxidizing agent, what am I going to ask for?
The one that's reduced.
Okay, the one that was reduced. So what's my answer?
Nitrogen.
Nitrogen wasn't added to this reaction, so it can't possibly be the agent. For those of you being like, what? Nitrogen was definitely added. No, it wasn't. Where do you see nitrogen all by itself? It isn't. Nitrogen was not added to the reaction. It cannot be the oxidizing agent. What is the oxidizing agent? Careful. The nitrate. NO3 minus was the one that was added. So our agent will be the species that contained the element or that did the opposite thing. So in this case, our oxidizing agent is the compound that contains the element that was reduced. Right? That is a very subtle nuance behind it. I have asked that question in the past on an exam. I don't think I ever will again. Okay, but it is a good question to ask. Does that make sense?
Yes.
Okay. Talk to me after class. Cash me outside? Sorry. Wrong one. That was horrible. I apologize. that was. I really shouldn't have done that. I should not be giving them more support. Next. Let's just stop digging. If we looked at answers, we could see the answers to each of these because I did publish or put those answers up on these slides. If you don't see them right away when you open up, I think they are visible. Okay, I don't think they're hidden behind a magic white box. So if you look at the PowerPoint slides, you should find these. Okay, a lot of people get tripped up by the sodium bismuthate. This one becomes tricky because you aren't familiar with the BiO3 compound. That's a complex ion. Sorry, that's all I can say. I wouldn't ask it again. Okay? But we could go through and do the same kind of process behind each of those.
How would you do the equation for the bismuthates? Or would it be 3 variables?
So with the sodium bismuthate, that's the one that trips people up. We could go through and try it with 3 variables. We wouldn't be able to solve it. Sodium is? Sodium is? I'll accept a +1. How do we know it's a +1? How do we know it's plus? It's a metal. Oxygen is? What kind of bond are we looking at here? Ionic. If it's ionic, I can split it into the individual ions. Sodium metal with the bismuthate ion. If sodium's a +1, the bismuthate is? -1. I could now go through and solve for what bismuth is. Okay? Don't stress. I wouldn't ask that one again. That was a mistake putting it up there. Okay? So now the fun question that you've all been waiting for in balancing redox reactions. If I asked you to balance this equation, how would you do it? List out the atoms, and you would get the answer to be? Two is a good answer. Where are you telling me to put the 2? On the H+, and it would now be magically balanced. We don't have to worry about it. This is an example of a redox reaction. How do we know that?
Charges change.
The oxidation states change. Good fix. 0 to a +2. So we have transferred electrons in the course of this reaction. Notice again, the electrons haven't shown up in the equation. Because electrons are matter, we need to make sure that they balance. If we go through and test this one, we will find that the electrons do balance out, that everything's nice and fine. We didn't have to stress about dealing with electrons and all that nasty stuff. How about this one? Is that equation balanced?
No.
Why not? How many tins are there? 1 and 1. How many irons are there?
They're -1. So it is.
1 and 1. Is that balanced?
Yeah, it's balanced.
Yeah. How do we see our electrons? Where do they show up? In the charge. So let's evaluate our charge. Because our electrons account for that, we could see them balance out. What is the charge on the left-hand side of the equation? A +5. That usually trips people up. Does everybody get that, what we just did? Yes. Right-hand side.
6.
+6. Does the charge equivalate?
No.
Thank you for just accepting that. Okay, no. This equation, not balanced. Okay? If we tried that same thing with the previous one, you'd be like, well, the top one isn't balancing. Remember, we had to put the 2 in there, and we knew there was a 2, so the hydrogen's balanced, yeah? Charge on the left-hand side. Whoa.
3.
Try that again. It's a +2. Charge on the right-hand side. Try that again. +2.
Yeah.
The charges did balance for the first one. I didn't have to worry about electrons. For the bottom one,
Gotta worry about electrons.
I do have to worry about electrons. I have to make sure that when that equation is put together properly, that the charges do balance out. One quick fix for this. What would the charge now be on the right-hand side?
+5.
+5. Is the charge balanced?
No.
Yeah, +5 equals +5. That's awesome. Except
Is through an electron.
I have an electron in there. Are electrons allowed to exist on their own? No. So that's an invalid equation. I can't use it. Damn it. Okay? So we would have to come up with a different mechanism to balance the equation. There are a variety of ways to balance redox reactions. Okay? The way that I want you to be most familiar with is what is known as the half reaction method. Okay? In the half reaction, what do you think we're going to evaluate?
Half the reaction.
Half of the reaction. Which half do you think I should look at?
The reactants.
If I only look at the reactant side, how do I balance them? Well, I can't. There's nothing to balance them with on the product side. So looking at just the reactants or just the products won't work to balance. One of each. I'll take a look at iron balancing with iron. And I'll take a look at tin balancing with tin. Whoops. Because these are now half reactions, I can get a little bit of flexibility in my rules. I'm now allowed to bring electrons in. Because neither of these reactions can run on their own, I can use electrons to balance them to be an accounting method for making sure I bring them together. Okay? So let's use electrons to balance the first reaction. Where should I place the electron?
The product.
Why are you shaking your head? Why?
Oh, because if you add an electron, it's negative.
We have a +3 on the left, and now on the right we have a +1. Did this get closer to balancing or further? Further. Did we place the electron on the right side? No, I need to place the electron on the other side of the equation. Now what happens to my charge? Now the charges balance out. Good eye. And good for the wrong suggestion, because I needed that. Okay? Makes me feel smarter. Sorry. It's now balanced, so let's take a look at the tin. Is the tin balanced?
No.
What do we need to do?
On the
But I put it on the reactant side last time.
no, you have to put it on.
Put on the bigger side, the higher charge.
Could put it on the higher charge side. That's a nice way to do it. No one's actually pointed that out before. We'll place the electron on the higher charge side so that they balance out. +2, +4, -2 gets me a +2. I've placed the electrons appropriately. If I added these two things up, I would get the exact equation which said we could not end up with because I'd have a leftover electron on the product side. So when I deal with these equations, I need to make sure that when I put them together, the electrons cancel. Kind of like what we did when we were trying to cancel out electrons on individual atoms, on canceling out their charges. Right? What is the lowest common multiple between 2 and 1? 2. How do I make a 1 into a 2? I multiply it by 2. But if I multiply that by 2, what do I have to do to the iron +3? And the iron +2? How do I make a 2, the blue 2, a 2? Multiply by 1. So that's a 2, that's a 1 and 1. Now what happens when we add these two equations together? So let's do the longhand version of this. 2 electrons plus 2 iron plus 3 plus 10 plus 2 plus 2 iron plus 2 plus 10 plus 4 plus 2 electrons. Yes? Just add everything up. Does something show up the same on both sides of the equation? Yeah. So if I said y plus x equals 4 plus y, can you tell me what x is?
4.
How are you telling me 4?
The ones cancel.
I can subtract y from this side, and as long as I subtract y from the other side, I do the same thing on both sides, those things can cancel out. Why am I talking about that as a relevant thing?
Cancel out.
The 2 electrons can cancel out. Bless you. Which means the equation becomes, it almost sounded like a drum roll. That was kind of cool. Does it look balanced?
Yeah.
Yeah, the irons balance out, the tins balance out. Do the charges balance out? What is the charge on the left-hand side of the equation?
I didn't do that. I didn't do the colors.
There's a 3 and a 2. It would be plus 5.
And it's gonna be,
It's a plus 8 on the product side. Plus 2 with the 2 there. I get a plus 4. Plus 4 is plus 8. Did the charge balance? Yes, this equation is now balanced. How do I ask it on a test? How many electrons were transferred in the course of this reaction? I don't know where you got 16 from or 8 for that. I do understand where you got the 8 from now. I don't know where you got the 16 from.
It's just 2.
How many electrons were transferred? How much did the tin give up? 2. How much did the iron eat? 2. How many were transferred? 2. Okay? And yes, the common conception, oh, I just add them together. No. I got rid of 2. I consumed 2. There were exactly 2 electrons transferred. Okay? If I give Frankie $5, he gets $5. Does that mean we transferred $10? No.
Wish.
Okay? Should have said it the other way around. Then I wish. Okay? That's the half reaction method. You break it into each of the individual half pieces and you process through that. Kinda, sorta? Okay. The next sequence of slides will be somewhat headache inducing, but it's walking through exactly what we just went through and did. Okay, and this is really what I want to hit on here before we leave, so you guys get some practice thinking about this. Okay, if I asked you, said 36 inches, how many feet?
3 feet,
What'd you do?
divided by 12.
Divided by 12. If I take 36 inches and I divide by 12, what do I get?
3.
I get 3. Does anybody see an F or a T in my work? No. What do I get? I get 3 inches. That doesn't make any freaking sense. Exactly. When you said you divided by 12, what you have done is created an algorithm to solve this quickly. That's phenomenal because you've used those calculations lots of times before, and that's great. That's fantastic. Repeated calculations, almost always, we want to create an algorithm for so we don't have to think. Okay, that's why we do it. The problem with that is what happens if we switch now to a unit system you know nothing about. You have no clue how to solve. Okay? This unit is a big struggle back and forth between me and you. Okay? And what it comes down to is you're like, but all I did was divide by 12 and I got the right number. I don't care about the number, I care about the unit. And dividing by 12 does not get me the right unit. Okay? That work is invalid. And it will not work through the rest of the semester. Okay? So that's fantastic that you can do that. And I'm not going to debate that you can do that. But what I want you to do is starting to think about a process so that when we shift to a unit system that you have not created an algorithm for, you can solve those questions without understanding that material quite yet. What do I mean? How do we actually solve this?
You mentioned this.
Oh, using a ratio.
This is dimensional analysis. What am I doing? I'm multiplying by 1. The 1 I'm using allows those units to cancel out to set up the proper system. The textbook calls this, what do they call it? The factor label method or unit analysis. It's dimensional analysis. It's all the same thing. It has 3 steps. Number 1, know where you're going. Write down what you want for a final answer. Unit. Number 2, what information are you given? Number 3, start inserting unit factors, okay, or picked ones that allow for that unit to convert. The point of this section is for you to go through and solve it the way you think you want to solve it. That's cool. Then solve it my way. Prove my way works. That's all I want you to do.
All right.
Once my way works and you believe it, when we move into the next unit and you fail miserably with your way, you can fall back on my way.
Good to know.
That's it. We'll pick up